Dr. Jennifer Gaduba is an associate scientist with the Wilson Fellowship, or with the Wilson Fellowship at the Fermi Lab in the US. She's leading the facility for particle physics research in the application of AI to particle physics towards more intelligent detector systems, data reduction, data analysis strategies, and this ensures the efficient extraction of the most fundamental physics information from the multitude of data collected at the LHC, so the Large Hadron Collider, at the world's highest energy particle physics experiment, which is located at the CERN laboratory in Switzerland, or on the Swiss-French border. Now, Jennifer co-founded the Fast Machine Learning Organization. That's a research collective of physicists, engineers, and computer scientists interested in deploying machine learning algorithms for unique and challenging scientific applications. And she's also applying modern anomaly detection techniques to advance the quest for elusive new physics at the LHC. So just before I hand over to Jennifer, just as a reminder, we get to use Slido for question tracking. And so if you've got a question, please go to the Slido link that the organizers will have put into the chat and write your question, but also please put the name of the speaker that you wish to address that question to in the chat. And so with that said, over to you, Jennifer.
Thank you, Adrian, for the introduction. Let me share the slides. I need to close the. Okay. Thanks a lot again for the introduction. Thank you also for inviting me to give this talk at this interesting seminar series. We'll give an overview of machine learning applications in high energy physics. Let me first set a little bit the context. So where we stand today in particle physics. The beginning of this century marked a big expansion of our knowledge of the universe from the very small to the very large scale. And two of the main highlights of the last decade was the discovery of the Higgs boson in 2012 by the experiments at the Large Hadron Collider at CERN, and the direct observation of gravitational waves. So we, let's say, feel like the missing pieces of two of the most successful theories in the history of science, so the standard model of particle physics, explaining fundamental interactions, and general relativity, explaining or describing, say, astronomical phenomena. There is still a lot that we do not know. In particular, the standard model doesn't account for neutrino masses. Gravity is not included in the theory, and the standard model explains only 5% of the universe, as there are no standard model candidate for dark matter, and also doesn't account for matter-antimatter asymmetry, which caused the universe to be as we see it today. So these are fundamental questions, and to answer to them, we need complex devices. We build complex devices and the big collaborations on infrastructures and new technologies. So this is discovery science that needs indeed the same innovations that drive your daily life in the big data era. Machine learning, we know it's a pillar of innovation when handling big data, which goes across domains. In fact, we apply industry advancements in science for the we're applying in science industry advancements for the society to our particle physics problems. But at the same time, particle physicists also drive the innovations that have impact in the society. At the energy frontier, we have the Large Hadron Collider at CERN. CERN is a laboratory located part in France and part in Switzerland. And so in the collider, we collide the protons at an extremely high frequency, 40 million times per second. And consider that there are several collision points along the ring, and at the time the protons collide, this creates other thousands of particles, which by studying the products of these collisions, we did hope to answer some of the questions that I mentioned before. So now, to reconstruct all these particles, we have detectors around the collision point, which are made up of tens of millions of channels. And so you can imagine with some calculations that we are dealing with extreme data rates of petabytes per second. The situation become even more challenging in the last decade. In fact, since the discovery of the Higgs boson in 2012, we kept, let's say, upgrading both the collider and the experiments. But the big upgrade will be the high luminosity LHC run. In fact, the collider will be upgraded to basically increase the luminosity of the beams in order to increase the statistics of seeing very rare processes. And in order to cope with indeed a more complex collision environment that we will have with the upgrade of the accelerator, the detectors will also undergo very important upgrades with an significant increase in number of readout channels. So you can imagine that given these upgrades, the event complexity will increase, and so the computing resources and disk storage needs for the experiments. At the intensity frontier, we have experiments studying neutrino oscillations. We have built and run several in the past, and some are still running, but there will be the next generation will be the deep underground neutrino experiment, which I'm going to explain a little bit its functionality. So this detector is now under construction and R&D to start operations also in the late 2020s. It's a massive detector, 1 mile underground, comprising 70 kilotons of liquid argon and advanced technology to record neutrino interactions with extraordinary precision. So it is located at 1,300 kilometers from where the beam is created, the beam is created at Fermilab. And so the FAR detector is actually in South Dakota. You might wonder why. Well, because neutrinos rarely interact with matter, and so the path, so that the traverse needs to be very long in order for them to interact and see these different interactions in the liquid argon detector. In particular, we hope to study with high precision the oscillations. So we know that the neutrino beam, when it's created at Fermilab, is populated by some flavor of neutrinos, and then after oscillating, we expect to see a different neutrino flavors. Also, this detector features uncompressed continuous readout of modules, which will yield tens of terabits per second, and this is unprecedented for this type of experiment. So we build these complex devices to answer to our fundamental questions, and in particular, we think that new beyond the standard model particles could explain this. If yes, then they will be produced directly in proton-proton collisions at the LHC, or be inferred from precision studies of neutrino interactions at Dune. However, finding the answer by analyzing this complex data could be extremely challenging. That's why we look at machine learning, or we have looked at machine learning in the past, and more recently on modern, let's say, deep learning, because we know that it scales well with the data complexity and also can extract the most useful information from very complex data. So there is a huge amount of exciting R&D, which is impossible to cover in 20 minutes. So, but there is a page where you can consult. I'm also happy to provide more insights on some specific problems if needed. So we know that the machine learning accelerates scientific discoveries. So, for example, played an important role in the discovery of the Higgs boson 10 years ago. In fact, we studied the Higgs boson first in its decay into two photons, and we see it by identifying events that have two photons, and then we reconstructed the invariant mass. And while the background is smoothly falling in red, as can be seen here, the Higgs boson appears instead as a bump on top of it. It sounds like easy, but actually, like the identification of the two photons and also the precision measurement of its invariant mass require specific algorithms. At the time, back then, that was 10 years ago, we're mostly using boosted decision trees, which were popular in HAP, and that's what actually helped us indeed seeing being able, that would help us making this measurement. Today, today we use modern deep learning to expand and consolidate the knowledge on the Higgs boson properties, and this enable or accelerate our ability to access and study a range of physics phenomena that involves the Higgs boson. One major success of deep learning HAP is jet identification at the LHC. So jets are a spray of hadrons initiated by a fundamental particle of some kind. Then these hadrons get clustered into one object called a jet. And the jet can have different properties depending on the mother particle. So identifying a jet, which is also what we call jet tagging, is like answering to the question, who was the mother particle? So for example, the Higgs boson decaying to bottom quarks is a very challenging signal to be seen, and that's why we need these jet identification techniques, because by that we can identify, as you see in this cartoon on the right, that a jet coming from an Higgs boson has two structures which derive from the two initial quarks. But instead, the background jets, which are actually overwhelming, like orders of magnitude higher in rate, are characterized by one structure, which comes from the single quark, from the initial single quark or gluon. So what we need to do is to reject as much as possible the background and keep as much as possible the signal. So we studied a multitude of algorithms for this, from human level analysis of physics observables to deep learning. And in deep learning, we studied, let's say, first shallow neural networks based on high-level features, and then deep neural networks based on raw-level features. And in particular, we studied many different LHC physics data representations, images, sequences, and point cloud. And actually, we learned by studying jets, actually, that the point cloud representations and architectures are the most promising, or actually are able by construction to capture the sparse, heterogeneous, and permutation invariant structure of HAP data. And I think this was a crucial breakthrough in the application of machine learning to particle physics. And in fact, we are using now, let's say, this representation in many different tasks that require indeed understanding the physics structure of the data. So actually measuring the Higgs boson decaying to bottom quarks was kind of unthinkable 2 years ago. There is just too much background to get rid of with standard methods, but nowadays with this indeed modern deep learning based tagging algorithms, we start having evidence for it. And this gives us confidence that even more challenging and more rare, say, beyond standard model topologies can be found in this way. Also, most recently, we started focusing on unsupervised learning as, let's say, the next paradigm in searches, or not next, but let's say parallel approach in searches. In this case, you do not specify a signal up front, and so you fully train on data without relying on simulation, and try to detect outliers from the main distribution of the background. So this gives this approach, we rely less on theoretical motivations, because new physics indeed could be anywhere we had not thought of. So LHC is not the only say, application of machine learning in particle physics. I just mentioned before the Dune experiment, which is actually the next generation of neutrino experiments. But there are, NOVA, for instance, is in operation since 2014, and also aims at studying, making precise measurements of neutrino oscillations, similarly to Dune. So the path detector in this case is like 800 kilometers from Fermilab, where the beam is created, and it comprises 14 kiloton of liquid scintillator for say more than 300,000 channels. So when the neutrinos interact with the nucleus, they create charged particles whose energy is absorbed by the material and made visible by emitting light. So then the pattern of light seen by photodetector cells is used to determine the neutrino type and energy. So here is an example of how neutrino interactions look like in this detector, and there are several different ones, from charge current and neutral current interactions. So actually, NOVA was one of the first applied machine learning to identify neutrino interactions. In fact, as you can see from these images, are very are regular. So they, by represent, so basically the experimental data themselves are regular and can be depicted as images which represent the two-dimensional projections of energy depositions. So they're suitable for computer vision techniques. And in fact, with GoogleNet inspired architecture, they improved the physics performance with a gain that is equivalent to 4.2 kilotons of additional detector mass. So with respect to traditional particle identification algorithms. So this is a very promising precedent for application to newer generation, larger scale and higher resolution experiments based on liquid argon. So big data in this let's say era of very complex devices, experiments, means increasing the need for efficient and accurate data processing for high throughput applications. And as you can see in this, so this plot basically shows an extrapolation of the computing, so of the total CPU needs at, let's say, in the next decade at the high luminosity LHC. And the dashed line in particular show the, the solid line is what we would expect to, what our needs will be in terms of computing if we do not do any R&D. So if we just apply our paradigms that we have today. And that indeed is not contained in the gray band, which represents the computing resources that we will have available with the 10 to 20% annual resource increase. However, by doing R&D today, we can actually go back to we can actually be within this budget. So that's because of this. We are now putting a lot of effort to replace non-scalable standard algorithms with machine learning based ones, and also to adapt computing infrastructures and software to take advantage of heterogeneous platforms that could feature accelerators, so like GPUs and FPGAs. Just to show you what's actually the, one of the most expensive workflow in HEP, and that's the simulation. In fact, the HEP experiments rely heavily on simulations, from experimental design all the way to data analysis. So in this pie chart from Atlas, you can see that the Monte Carlo, the full simulation, plus the event generation is like 40% of the total workflow. And in fact, this workflow is a major and growing bottleneck at the LHC and other experiments. So this is one of the parts of the workshop in which we're putting efforts in replacing the very accurate GENT4 workflow, which however is very slow, with the surrogate model, which allows us to generate less events as input, but to generate way more as output and way faster. And this surrogate model is what can indeed be represented by machine learning methods. And in fact, there is a lot of work in studying generative adversarial networks and variational autoencoders and normalizing flow to understand how to make it as accurate as possible. Now, this is like the final, let's say, application I wanted to talk about, which is machine learning for real-time data processing. So depending on the data rates, there is like some, so it's important to apply some amount of data reduction. So the LHC, it's in terms of, let's say, of data rates flowing out of the detector, is one of the most challenging. We're talking about petabytes per second flowing out of the detector. And so you can imagine that we cannot keep, we cannot process all of them without like a huge amount of computing resources, and so we need to apply some amount of data reduction, and that's the task of the level 1 trigger, which is actually the first stage in this data reduction workflow. However, because there is a limited buffering on the detector at this enormous data rate from sensors, there is only a few microseconds available to perform a coarse analysis of sensor data and apply rules for event filtering in real time. And that's why in this chart, the ellipsis is the most challenging and way to the left in terms of latency, in terms of available latency. The system, so this trigger system, since it has to be like very, very efficient, consists of pre-programmable gate arrays and custom hardware. And also, we have a limited amount of them because this is constrained by the experimental system. So I would say that this is the ultimate challenge in application of machine learning. Also, I like to call it ultra-fast machine learning. But however, if you look at this again, at this chart, this graph, it's not the only let's say, experiment that is in need of some type of data reduction in real time. And actually, there is a growing need for fast and efficient machine learning in science. So actually, that's where particle physicists made a big impact. In fact, these unique needs brought together a community of scientists from very different domains that attracted, say, the outside world of AI researchers in both academia and industry. We created the Fast Machine Learning Lab, holding interdisciplinary yearly workshops. Actually, the last one was just 2 weeks ago. And the concept behind this community is to bring together domain-specific challenges, machine learning, and experiment and computer system architectures to accelerate the discoveries in science. So there are many challenging tasks in HAP, that need indeed machine learning that can get a lot of help from machine learning developments. However, machine learning is rapidly growing largely outside of particle physics. At the same time, our unique challenges need new expertise, knowledge, and resources to indeed solve these challenges. So we also think that across scientific domains, together with the outside world, we can contribute to the advancement of machine learning itself and other related applications. So quoting Nyan at SNOMAS, we need to capture the interest of non-HAP collaborators. And how do we do it? Well, the physics mission is beautiful and engaging. And we have unique aspects, as I said, many challenging tasks that could push the bounds of machine learning research. This brings me to my conclusions. The physics, so the scientific mission is to answer the fundamental questions about the universe with very advanced particle detectors. There are enormous challenges due to the large volume of data and strict experimental system constraints. Machine learning offers solution because of its scalable capabilities, but not without an intense effort to change our approaches at every data processing stage. So it's important to promote interdisciplinary collaborations among physicists, data scientists, computer scientists, and also engineers, and to promote education and training at the intersection of these disciplines by evaluating scientific computing research, by cultivating dedicated spaces and content, and also by supporting students learning these skills and create opportunities for researchers to stay. Thank you.
Thank you very much, Jennifer. It's an inspiring talk and a difficult one to cover such a broad array of application of machine learning. So you did a great job there. I think moving on, we'll continue to collect questions in Slido. And so everyone who's been listening to Jennifer's talk, if you've got questions for her, please continue to post them in Slido. We'll come back to the questions at the end, just to make sure that everyone has the ability to enjoy the next speaker's talk as well, and to reflect a little bit on what you're hearing from the speakers. So we'll thank you, Jennifer. We'll come back to you with questions shortly. Moving on now to our next speaker. So our second speaker is Dr. Jim Halverson. He is an associate professor at Northeastern, University in Boston, Massachusetts. His research focuses on the interface between string theory, particle physics, cosmology, mathematics, and deep learning. And he's particularly interested in the string landscape and its implications for particle physics and cosmology beyond their standard models. And these implications often follow from the structure of extra-dimensional geometries, of which there are many possibilities. His research, therefore, requires importing techniques from mathematics and computer science. And recently, he's been working in the interface of physics and deep learning, and that his interest in this area has continued to grow. And to that end, he's now the co-PI and serves on the Institute Board of the NSF AI Institute for Artificial Intelligence and Fundamental Interactions, and co-organizes the physics of the intersection between physics and machine learning. And with that, just as a reminder, everyone, please use Slido to post questions, and indicate whether that question is to both speakers or to Jennifer or to Jim. Over to you, Jim.
All right, I hope everyone can hear me okay. First of all, I'd like to thank the organizers and Jennifer and Adrian for this wonderful opportunity to have a discussion about machine learning and high energy physics. I am a theorist, but I'm a theorist with broad interests. So I wanted to sort of speak broadly about machine learning, which itself is a broad field, and high energy theory, which is also a broad field, and try to give you a sense of some of the things that are happening in the field that is emerging over the last 5, 10, 15 years. As was already mentioned, I am thrilled to be a part of the NSF AI Institute for Artificial Intelligence and Fundamental Interactions. This is a Boston-based NSF AI Institute. We have lots of activities and lots of opportunities, and you can check out our website if you're interested in connecting with us. So what I want to do today is to give you a number of examples of different types of machine learning that are interfacing with different aspects of high energy theory and pure mathematics. Some of those examples may hit home with some of you, others with others. But as I go through the examples, what I'd like you to see is that there's a theme sort of running through the talk as a whole. In particular, I want to give you an overview, a potential pitfall, and also talk about a potential opportunity in this direction. So one thing as a theorist that is different about us is that generally speaking, I am not working with experimental data. So if we're talking about machine learning for theoretical physics, how is it that our data differs from other types of data that are out there? That's an overview I'd like to give some examples of ML in that context. In particular, because this is about theoretical physics and in some cases about pure mathematics, which is another interest of mine, you might ask, aren't these fields that care deeply about rigor and understanding? And how do we square that idea with the fact that machine learning techniques are often stochastic, error prone, and black box? And finally, at the very end, I'll have one slide on what I consider to be an exciting opportunity, which is ways in which progress in ML theory instead of applied ML could potentially interface with high energy theory and with pure math. So first of all, ML for high energy physics theory, TH throughout. What types of data do we have? Well, something that is different about our data, generally speaking, is that it's often defined by definitions, which sounds like a little bit of a funny thing to say. So I'd like to run through some other types of data that are out there. Here's a picture of Bono, and a lot of machine learning applications use images in various ways. And this is data, if you would like, that is meaningful on Earth, in the sense that we can all recognize Bono or images of human beings, but if you imagine some world where you were able to contact some distant civilization and you showed them an image of Bono, they probably wouldn't recognize exactly what he is, and they certainly wouldn't know that he's the singer of U2. So this is exciting because this is something that's local to Earth. This is experimental data that's local to Earth, and it is meaningful because it affects our lives in various ways. I'd like to contrast that with what Jennifer just talked about, which is particle collisions. This is a fundamentally different type of data. If you'd like, this is universal experimental data in the sense that the standard model of particle physics is translation invariant. So particle physics as we know it, if you were to carry it out in a different galaxy, would be the same. And so in particular, some distant civilization might have access to this same data, even though they don't have access to Bono. So that's universal experimental data. Finally, the types of data that my friends and I like to deal with, for example, the standard model of particle physics, is what I would call universal theoretical data, which I would say is meaningful everywhere in the sense that you could take it to some distant civilization, and if they had come up with the same definitions and axioms for their mathematics, it would logically lead to the same conclusions because it's axiomatic and rigorous. So they might have this data even if they don't know who Bono is. So these are the different types of data, and these are some of the sorts of things that high energy theorists are thinking about. So in some sense, our data is different. We have a number of problem types and examples that are of interest to us. One of them, which Jennifer talked about a little bit, is what I would call data prediction. So many times in machine learning, we want to be able to predict some aspect of some scientific system. The buzzword for this in machine learning is supervised learning. And an example is in particle collisions, there are often these jets that emerge. And when you see one of these jets, and theorists and experimentalists both study these, something that you're interested in doing is predicting whether the origin of the jet is coming from a quark or from a gluon. This is supervised learning. It's about predicting, given the image, did this come from a quark or did this come from a gluon? On the other hand, something that is also interesting, Jennifer also talked about generative models, is data generation. I have some friends that are very, very good at something called lattice quantum field theory, which is a non-perturbative numerical way to do computations in strongly interacting quantum field theories. And recently, there's been a lot of work in this direction using generative models to try to make progress in this field. So in particular, what they do is they take some noise and they push it through something called a normalizing flow. And what it generates is a good lattice field theory configuration. That is a lattice field theory configuration that is from the right distribution, so to say, as dictated by theory. And so what this allows is a machine learning technique that actually generates the data, if you would like. And what this leads to is better numerical predictions for the structure of quantum matter. Another type of problem that you might be interested in, you might use common words like search or gameplay. The buzzword for this in machine learning is called reinforcement learning. If you followed the stories out of DeepMind in recent years having to do with Go and chess, the type of machine learning that they use is called reinforcement learning. And the basic idea is that an artificial intelligence agent, you train it in a particular way such that it has some set of actions that it knows how to take. At the beginning of its life, it is not very good at choosing actions, but by playing many, many games, it updates how it chooses actions such that it becomes well-behaved over time. And so we applied this to string theory and obtaining consistent theories in 2019. And more recently, it's been applied to particle physics model building, namely the sorts of games that string theorists and model builders like to play. Can you teach an AI to do it? And at least in certain contexts, the answer is yes. So that's interesting. Those are some of the problems that we have. We have data that is generally defined by definitions. There are many different types of machine learning. There are many different types of problems in theoretical high energy physics. And we're in the process of figuring out what is a useful map between these fields. But something that's also true in theoretical physics and pure mathematics is that we care deeply about both rigor and understanding. And so one pitfall that is a potential pitfall, and I'd like to talk about how to mitigate it, is to answer the question, how are we supposed to get rigor and understanding from techniques that are often stochastic, error-prone, and black box? So as an example, I'd like to give you an example of the error concern. Some of you may have seen this example before. If not, I hope it's interesting to you. So supervised machine learning, which remember is about predicting things, it's not 100% accurate. It usually has some error associated with it, which if you're trying to do theoretical physics or pure math is generally something we try to avoid at all costs. And in particular, it not only has error, but it can even be attacked. So there's this very famous example from 2014. A convolutional neural network was trained to take in images and predict what is in the image. So in this particular case, the trained neural network is fed this image of this panda. And it says that it's a panda, but it's not sure that it's a panda. It only has 57.7% confidence that it is a panda. So already there, before I explain the rest of the slide, the neural network is getting the prediction correct, but it's not sure. And in particular, you might be concerned that it's not sure because to human eyes, this is very clearly a panda. So what this paper did is that on top of this prediction of the panda, they took a little bit of noise drawn from some distribution, and they superimposed it on the panda such that the superimposed image still is this. This is technically a different image than this image, but to a human, this is obviously still a panda. But nevertheless, in via this noise perturbation, the neural network actually gets the answer wrong, and it's quite confident that it's wrong. So with this image, it thinks that it's a given, and it has 99.3% confidence that indeed it is a given. So not only can supervised machine learning have error, but the error can be attacked. It can be subject to so-called adversarial attacks. And this is one of the things that we run into, this sort of problem, when we're trying to use machine learning in subjects that require rigor and/or understanding. So how do we avoid it? Well, this is something that is still the subject of much research, but a couple of ideas are emerging. One of the ways for avoiding error is what I would call conjecture generation. The basic idea is that you use some machine learning algorithm, for example, one of these supervised learning algorithms. You study correlations once it's trained. From those correlations, when you bring the human into the loop and have some domain expertise, it might lead a human to recognize that something special is happening, and the ML algorithm and the discovered correlation might lead the human to generate a conjecture. And once you have a conjecture, now we're entering the realm of math, and you could try to take that conjecture and turn it into a theorem. So this is something that my group was interested in 2017. My collaborators and I worked in a particular string context. Apologies for the knot theory glimpse. What we had was samples from an ensemble of 10 to the 755 extra dimensional manifolds that arise in string theory. These are interesting for a variety of reasons. But what we used was simple supervised learning and interpretation to try to answer the question of whether particular types of particle physics models arise in this context. And what we were able to do was to, using supervised learning, it was getting very good accuracy, but we were able to open the box because we used simple algorithms, write down a conjecture, and then turn it into a theorem that gave a simpler understanding of how this particular particle physics model arises in string theory. So that's one type of pipeline you might use. There was a very exciting paper out of various mathematicians from excellent universities and also DeepMind last year that was applying a similar technique in the context of knot theory. This was a Nature paper. First of all, I'm going to say a little bit about knot theory. So let me tell you that this is the simplest example of a non-trivial mathematical knot. You can see that this is some sort of string that has been tied together in three-dimensional space and projected onto the plane. And one thing that's a fact about this is that you cannot turn this knot into a simple circle without ripping and tearing it. It is a non-trivial knot. So what happened in this paper is that there was a database of mathematical knots. The technique that was used was supervised learning with neural networks and a technique called gradient saliency, which allowed the team to try to understand which variables were most important to understanding the topology of this knot. This led the mathematicians, the topologists that were the experts on the collaboration, to generate a conjecture and to turn it into a theorem that was a new relationship between geometric and algebraic topological invariance. So this is a lot of jargon, but what I would say is that a topological invariant of a knot is some property of the knot that never changes if you just deform the knot without ripping or tearing it. And there are fundamentally different types of topological invariants, so-called geometric and algebraic topological invariants. And so this was a surprise that these seemingly unrelated things had a particularly simple relationship that could be turned into a rigorous mathematical theorem, beginning with machine learning, but then bringing the human into the loop. Another thing that one might do is to try to avoid error is to try to do what I would call rigorous solution verification. So in reinforcement learning, which I would remind you is this type of machine learning where we have gameplay, where an agent learns to take an intelligent sequence of moves, the trained agent may stumble upon, via its training and getting good at some particular goal, it may stumble upon a sequence of moves that gives you an endpoint of the game, so to say, that allows you to rigorously verify some property. So I'm presenting a knot theory example again for the sake of pedagogy, because this is something that I think is pretty easy to appreciate. So there's a famous problem in knot theory that is a fundamental problem, perhaps not the most advanced problem. There are more exciting problems, but it's called the unknot problem. And the problem is this: given a knot, you want to ask the question, can I deform this thing into a circle without ripping or tearing it? It turns out that you can deform this into a circle without ripping or tearing it, but this knot, which is called the trefoil knot, cannot be deformed into a circle without ripping or tearing it. So that's the question of the unknot problem. Can a given knot be deformed into the circle without ripping and tearing? And mathematicians have a rigorous set of moves that lets them characterize whether this happens. There's certain moves that you can do to the knot to try to turn it into a circle, and we know a lot about those. So what you can do is you can take a machine learning treatment approach to the problem where you have the reinforcement learning agent have these moves accessible to it, And what it does is it trains on many, many examples of knots, and it learns how to choose those moves intelligently so that it can try to simplify the knot as much as possible to try to demonstrate that it is indeed a circle, or the unknot, as we say. What this result shows from this paper in 2020 is that reinforcement learning is finding sequences of moves that is indeed turning this into the circle. The green dots are a random walker. The x-axis is sort of the complexity of the knot. And what we see is that these two reinforcement learning algorithms, which are in blue and in orange, are significantly outperforming the random walker in terms of the accuracy. The point that I'd like to make, though, is that once you have such a solution discovered by reinforcement learning, it is a rigorous solution. You can hand it to a mathematician, they can check it and verify that indeed from machine learning we're getting a rigorous result. And finally, the last thing that I'd like to say, which I think is an exciting opportunity, is that we often apply machine learning in high energy physics and in more broadly in STEM fields, including my field, which is theoretical high energy physics. But machine learning theory is also advancing in recent years. And it's natural to ask whether machine learning theory is bringing new perspectives to high energy physics and to mathematics, aside from the exciting applications that I would call applied machine learning. So something that is growing recently is using machine learning theory for high energy physics and for mathematics. There's something that my group is deeply interested in, which we call the neural network field theory correspondence. This is a new approach to field theory. Quantum field theory is the bedrock theoretical foundation that underlies the standard model of particle physics. And in this new approach to field theory, the field theory is defined not by an action, as we canonically do in Feynman's description of field theory in terms of a path integral. It's defined instead in terms of an architecture, and all of the details of the architecture are encoded in this symbol here. So in particular, this is the canonical way that we do Euclidean field theory. But this is the way that neural networks suggest to do field theory. And this is a dual description, a different description of a partition function. And you can do computations in this framework that sometimes are inaccessible in this framework. So many ideas in field theory that we know and love from understanding particle physics systems, condensed matter systems, et cetera, are starting to emerge in this neural network context. For example, my group wrote a paper on symmetries. But basically, this is a rethink of field theory in the context of neural networks. It touches onto things happening in the machine learning literature, and there's also some things emerging in the physics literature as well. So this is something that I'm particularly excited about. Aside from that, you might ask if you can use neural networks for differential geometry. So these Calabi-Yau manifolds that you may have heard of that form the extra dimensions of string theory, there's a dirty little secret that we don't like to admit. Compact Calabi-Yau manifolds, which are the ones that are potentially relevant for four-dimensional physics, they're defined by a certain type of metric. The metric is an object that tells you about distances on any manifold. And what we know is that there's a theorem that guarantees that that certain type of metric exists, but there is not a single known analytic example of that metric in a compact setup with particular assumptions that are relevant for four-dimensional theories. So we know that the metric exists, but we actually don't know a single example in the cases that are of most interest. So this is something that we don't readily admit because it highlights some of the things that we don't know. Even though that is true, there are still lots of things we can compute in this context. But something that came out a couple of years ago is, instead of trying to come up with analytic solutions for the metric, to try to let the metric be modeled by a neural network that you then train, and hopefully after the training procedure, you end up with a good approximation to the metric that we care about. So these are some of the papers that did that. What they get is state-of-the-art, it's a state-of-the-art numerical Calabi-Yau metric arising as a flow in the space of metrics. And one idea that I'm excited about is that in machine learning theory in recent years, we have understood, not my group, but other groups have understood flows in the space of neural networks from a theoretical perspective, and they've gotten a lot of analytic control over that. So if we understand flows in the space of neural networks, but we model our metric as a neural network itself, then you can ask, how does the flow in the space of neural networks induce flows in the space of metrics? And you can bring in something called neural tangent kernel theory that is uncovering various different things that I find very exciting. So for example, improving the Poincare conjecture in 3 dimensions, Perelman reformulated Ricci flow in terms of a scalar action functional that is related to the loss function in machine learning. So this very famous result of Perelman can actually be realized as a subset of the possibilities that we can get in machine learning. So just to review, and then we'll take questions. The overview is that in my field, data is generally speaking arising from definitions. rigorous definitions that you could take to some distant civilization, and they might have the same data because they might have the same definitions. There are many different problem types and machine learning approaches. A pitfall that we generally have to worry about and try to mitigate is how are we supposed to get rigor and understanding from techniques that are stochastic, error-prone, and black box. And the opportunity that I mentioned at the very end is to not just apply ML, but to bring ML theory into the ways that we think about theoretical physics and pure math. My concluding thought is that machine learning is a young field compared to theoretical physics or pure math. This is a good thing. It means that we should take a broad approach to connecting the fields since we're just beginning to understand the impact of ML in theoretical physics and in math. Here are some various ways to connect if you're interested. I'll leave this slide, these slides will be posted so you can come back and see those if you want to connect. And thank you very much.
Great. Thanks very much, Jim. So this is Zainab is posted to everyone in the list. We now have a 20-minute Q&A session. Please do submit your questions to both the speakers in Slido. I'm going to use my prerogative as chairing this session just to ask one or two questions to warm up, and that hopefully will give people a little bit more time to think about some questions that have come in. And so to both speakers, maybe Jennifer first, and then over to Jim. When did you start using machine learning for your research, and what was it that motivated you to go in the direction of applying machine learning methods?
So for me, I started when I realized that that it's needed to be able to let's say achieve our physics goals at the high luminosity LHC. In particular, I got interested in the trigger and realized how fascinating it was to actually bring it to this, let's say, very ultimate challenging application of the real time, in the context of the real time data acquisition. And so that was because I know that at the high luminosity LHC, the trigger is like the ultimate factor in say being able to collect good data and make something the best out of it. Yeah.
So in my context, something that string theorists have really learned over the last 20 years that in other contexts was a little obvious is that there are many, many possibilities for the theories, and in particular, the so-called vacua that arise. At the same time that I was getting involved in machine learning, my group had gotten our hands on a rigorous mathematical object that would generate, it was an algorithm that would generate 10 to the 755 different string geometries. And we wanted to try to understand, if our vacuum, the standard model vacuum, is living in this context, what are some of the implications for particle physics or cosmology? But it requires really being able to grapple with this enormous set of different examples. And in particular, though I don't know the correct distribution, so to say, on that set of examples, I do know how to sample from uniform. And so in that distribution, I can sample these objects and I can study this enormous set of examples. But nevertheless, one needs to grapple with it directly. More broadly, that's just one example of a traditional problem that arises in string theory, that in trying to understand the landscape of string vacua, the numbers are enormous and the problems are complex. And so we had better be more sophisticated about our computer science than just brute force scans.
Great. And I think, I'll take the opportunity of asking one more question, and then we'll go over to the questions that are now appearing in Slido. So I think you may already have touched a little bit on this with your previous answer, but what do you think AI allows you to do that would otherwise be impossible? How has that changed the way that you approach research and the way that you work with others? Maybe Jim, you can start off giving an answer first, then we go over to Jennifer.
Yeah, absolutely. I admit I didn't expect when I started this in 2017 that ML would, turn upside down a lot of the ways that I think about things. And the last thing I would have told you that it would turn upside down is how I think about quantum field theory. So working in ML applied to physics has exposed me to communities that I would not have been exposed to if I sort of stayed in my previous lane. And we had some friends and I organized a meeting at Microsoft Research in 2019. And at that meeting, I learned that there's a particular thing in neural network theory called the neural network Gaussian process correspondence. And basically what that means is that neural networks at infinite width are functions that are functions from a Gaussian distribution over functions, a so-called Gaussian process. But something that is particularly exciting about that is that's exactly what free quantum field theories are. So in the limit, in the standard model, that you turn off all of the interactions, which in a particular context you actually can't do, but that's too technical. In the limit that you turn off interactions, you get exactly one of these non-interacting field theories. And these non-interacting field theories actually behave kind of like neural networks. So this inspired my group and other groups to sort of look at this correspondence between what's happening in neural network theory and quantum field theory. And it's led to a number of new insights. So I've been very excited about that and can say more. So.
Thank you. Jennifer?
Similarly, let's say to Jim, what changed for me is that I would have not expected to be able to collaborate with people from across disciplines. And I thought, okay, I'm gonna do, something that nobody cares, or let's say the outside world, or not that don't care, but that they maybe do not fully understand, or they think that we are some kind of elite. And instead, it was very interesting to be able to work indeed across both scientific domains as well as across, with industry as well. And in fact, so the work that we have done towards fast and efficient machine learning triggered quite a lot of interest. And so from that, we created very interesting collaborations like with Google and Xilinx. And also in the context of self-driving cars, but as well as in the medical treatments and brain research. So many different things. I think this is very exciting.
Thanks. So I think we should move over to questions from Slido. And the first one that comes up here is directed towards you, Jennifer. And it asks, is ML used in any production framework in the LHC experiments?
The answer is yes, it is. There are, for instance, the jet tagging algorithms that I was discussing before, as well as reconstruction of challenging objects like tau leptons, or also for the trigger, we already have something in production. We'll have more in the future. I would say though that there are the most challenging and most time, let's say, computing intensive tasks, which are, for instance, the track reconstruction, the reconstruction of the tracks, and of the calorimeter, which are very or more difficult, let's say, to achieve, more challenging to achieve in terms of accuracy. With deep learning algorithms, so we're not at that stage yet, but there is a lot of R&D. So these type of things are not in production, or like simulation workflow are not in production yet, because there is still work to do to achieve that type of accuracy that is needed.
Thanks. Then the next question is directed towards Jim, and it's more about the theory of machine learning development. So what caused recent progress in ML compared with previous decades of machine learning research? And what will limit this cycle of machine learning development?
Excellent, very interesting question. I should give two caveats. One is that I'm a physicist. The other is that, decades ago in the 80s and 90s, there was a lot of neural network research and I was a kid then. That said, I have followed what's been happening in ML recently very closely, and I've talked to a lot of people that are very detailed, have detailed knowledge of things that happened in the 80s and 90s. Without a doubt, one of the things that changed about 10 years ago was that levels of compute and auto-differentiation and backpropagation, the algorithms and the compute just got better. That allowed things that were known, like convolutional neural networks and other neural networks, to get pretty good accuracy on data sets. The field has grown from there. It's definitely not just compute. That is not the only thing leading to progress. So for instance, after that happened, more and more people came into the field, and people with physics and math backgrounds brought in ideas from physics and math. For example, symmetries have played more and more of a role. And one of the things that was shown in some work from last year is that when you take into account symmetries of your data and implement it at the level of neural networks, you actually get better scaling laws for how well things are going to learn as you increase the system size. So it's not just increasing compute, it's increasing compute and bringing in principles and having those principles affect the actual ML engineering. Then the other question is, what will limit this cycle of ML development? Some people might say it looks like there are no limitations. I don't know that I am so optimistic. But one thing that is true is that some of the most exciting things that are happening in language models, which many of you have probably heard about, so-called transformers, really requires enormous amounts of compute that, for instance, in academia, we typically just don't have access to those resources. So I was at a meeting at Harvard speaking in April, and there was a person from OpenAI there, and they were doing very advanced ML for simpler math problems, and I was doing slightly older ML for sort of PhD level math problems. And I sort of asked them, what would it take to train a transformer and on calculus textbooks, and have it go to calculus or something like that. And he quoted me some number of GPU hours on A100s. And then I said, how much would that cost? And he said, oh, it's about $500,000 or $1 million or something like that. And that sort of compute is something that is very hard to come across in traditional academia and traditional government funding schemes without a concerted community effort. Whereas at Google and Facebook and similar top tech companies, that sort of compute is more accessible. So definitely one thing I think will limit the cycle of ML development is that some of the compute that's required is really only available in industry.
So maybe, and this question, I guess, to both of you, leads into another question that's been posted a couple of minutes back. Have you implemented transformer attention networks in your work? So these things you can afford to do or have thought about or looked at?
I can comment on that. So this knot problem is related to a particular type of braid problem. If you have one of these knots and you cut it and you stretch it out, you can turn a knot into a braid. You turn the braid back into the knot by closing it off, and it turns back into a knot. So braids can actually be represented by so-called braid words, which is a string of integers, which is kind of like a sentence. So it's very natural to apply natural language processing and transformers in particular to problems in braid theory and subsequently in knot theory by the relation between braids and knots. So we did do that in an example in our 2020 paper. In that case, it was actually total overkill for the problem at hand because we did the transformer first and it did very well, but even a simple feed-forward network was already doing very, very well, like 95% accuracy on the problem. And so actually that's one of the pitfalls that I think a lot of people run into is that we often desire to apply advanced, super sexy machine learning methods to the problems at hand. But in many cases, those problems simply have not been addressed by modern computer science. And in some cases, they're just easier than we think. So that's me advocating, try the simple techniques first before you try to go state of the art with the architectures.
Jennifer, have you experienced or tried using transformer attention networks?
Well, yes, at the LHC, we're exploring those as well for jet tagging. That's one of the latest application, which actually also goes to the another question, right? What is the state-of-the-art architecture for jet tagging? And actually, indeed, that it's most recently a transformer type of architecture basically in which we try to incorporate say pairwise interactions in an attention mechanism. Yeah. These are there is also like for pileup mitigation, so it's another application that is being explored, but these are not yet in production.
Great. So I think we've got a couple more minutes for questions. So I've got a couple of other questions I'd like to ask if that's okay. Now, if you reflect on where you are now as innovators and leaders in applications of AI in your respective subfields of particle physics, what do you wish someone had told you about AI when you were starting out and learning how to apply machine learning to your various problems? And maybe Jennifer, you could address that question first.
Can you repeat it first? Because I think I couldn't understand.
So when you were starting out using AI, what do you wish someone had told you about AI when you were starting to apply that to problems that you didn't find in books or you didn't hear people talking about and that you had to figure out for yourself?
Well, that actually goes a little bit to what I was saying at the end of my talk. So when I started, so let's say that my generation of particle physicists was mostly physics, very little computing, I would say. And then you realize that, I mean, now computing is everything. The more we scale up the experiments. And so for me, there was a lot to learn. It's good that, I mean, I think it's good that you start from physics and then go to computing. But now I think it's, we need to train, I think we need to train indeed people, so, you know, young researchers a little bit differently in which, you know, like you study more like physics informed machine learning. So you get, when you enter into, then when you get into the, say in your career, you already have some basics. You don't have to learn everything because now just the world, the AI world is just gigantic, and there is a really, I mean, a lot first to learn and then to keep up with all the updates.
Thanks, Jennifer. Jim, do you have anything you want to add?
Yeah, I also wish that someone had told me and emphasized how gigantic AI and ML is. The reason is that as a physicist, you often sort of enter with your own little perspective and you try to identify one technique for one type of problem. But the problem is we have many problems and they're actually much bigger than my field, probably also much bigger than experimental particle physics. And therefore, you know, really grappling with how to apply ML techniques to physics requires just admitting how big they are. And part of admitting how big they are is saying some of what they're doing is going to be relevant and some is not. And you really kind of have to either have friends or become an expert yourself to be able to parse when should I apply an ML technique to a problem of mine and what particular type of technique.
Thanks. So I think there are a few more questions now in the chat. So there's one for you, Jennifer. So you talked a little bit about point cloud as the best representation since it captures the characteristics of the data. And the question's asking, could you explain a little bit more about what you mean by that?
Yes. So, let's say that in particular at the LHC, the experiments are so the detectors are heterogeneous. And so we have like a very high resolution inner detector, so inner tracking detector, and then we have coarser resolution calorimeter, and then we have like another part which is also different technology and different resolution. So it's very heterogeneous, and so like trying to, let's say, put with a hammer data that are heterogeneous into something like a regular type of grid, it's you lose a lot of information. And so that's why, and also not only you lose information, but also our data are very sparse. So when you start using images, you lose a lot of efficiency. So at some point we realized that instead of that we could be more efficient and extract way more useful information if we would represent the data in, like as points in space, because actually what we have in the detector are hits. So they're like a really point with the three coordinates, so let's say 3 coordinates plus the energy. And that's like, it's, let's say, the most natural representation rather than the regular grid, which doesn't represent the data. And also there is another let's say, aspect is the permutation invariance, because so for us, I mean, in particle physics, like a particle is indistinguishable from another particle that is the same. So you want the architecture to be permutation invariant as the physics is.
Thanks very much, Jennifer. So I think we're sort of running to the end of today's session, and so as we start the closeout, I'd like to just thank both of you, Jennifer and Jim, again for excellent talks and for the great discussion and your thoughts about the applications of machine learning to particle physics, both experimental and theoretical. And as we close today's event, I take the opportunity to remind everyone that our 4th and final event in the Nature Reviews Physics series which will be on machine learning research in industry. It starts at 4 p.m. UK time this time next week. If you look in the chat, you'll see that the organizers have posted a link to the Turing webpage where you'll be able to go and sign up for that event if you're interested. So please do sign up if you can. And there'll also be a feedback questionnaire that will be circulated as well by the organizers. And so please do take a moment to provide feedback so we can make events like this much more productive and better for everyone in the future. And thank you all for taking some time out of your afternoon or early morning if you're on the other side of the Atlantic, and enjoy the rest of your day.
Thank you.
Thank you very much.
Bye.
Thanks to the whole team and also to Adrian and Jennifer. Bye-bye.